Okay. So this is like four problems on this one. I've been teasing you with this a little bit last time. So what I want you to do in problem one is give me an example where you have a short exact sequence that doesn't split, even though the middle is isomorphic to the direct sum of the bookends. Now, when you start sniffing around and find such a thing, let me give you a hint. The modules have to be big in a certain sense. You have to have kind of a big module. It turns out that under certain conditions, the B is isomorphic to A sub C. I think like far as, for example, in theory and modules are finally generated, I think it'll work. So you're going to look at something where it's the modules are big in certain space. Number two, show that if I walk up to you on the street and give you any exact sequence like this, you can form it by splicing together a suitable number of short exact sequences. So in other words, you could take a short exact sequence involving an minus one, an plus one, and you can weave them together with compositions of maps to get you this, right? So a diagram might help you with this. Three, this is another, I want you to dig up another example that kind of, shows things can be weird. And so what's one of the things that you know about the vector space stage, right? Vector space, you had a basis, right? And what did you know about the basis, right? There's several things you knew about a basis. If you have a linearly independent set, you can expand it to a basis, right? That's one of the big things in linear algebras. If I walk up to you and give you a linearly independent set, you can sprinkle some fertilizer on it and make it grow to a basis, right? What else do we know about a basis? Well, if I have a four-dimensional vector space, every basis of that vector space will have four elements in it, right? The size of the basis, the dimension of the vector space is well defined. Here's an example that you should come up with. Let F be any field and B be a vector space of countably infinite dimension over F. Right? Make it easy. So B is just a infinite dimensional, countably infinite dimensional vector space over F. Let R be hom F B V. So R is actually the collection of F homomorphisms B to V. Translation. R is the collection of linear transformations. Now, you can compose these things, right? So this is actually a ring with identity. What is true about this ring? So it's not necessarily commutative, right? Well, it's not commutative, right? Because you don't expect function composition to work in both directions and get the same result, right? R is a ring. It does have an identity, right? But it's not commutative. Show that as a left module over itself, R is isomorphic to n copies of R for every n. So R as an R module is isomorphic to the direct sum of R and R. And actually, that's the big part to prove. Prove that R is isomorphic to R sum R as an R module. And then once you've done that, by induction, you can get everything else. So the big step is to show. So this is weird, right? This thing actually has a basis of n elements for every positive integer n, right? You got a basis one element, you got a basis two element, basis. So this is kind of weird, right? This cannot happen in situations that you're usually used to. Finally, I give you this definition, which is coming up soon. Consider the following diagram of R modules with the top row exact. By the way, look how fancy I think I am. What does the top row exact really mean about G? Yeah, yes, right. G is 1-to-1, right? So I just kind of did the intellectual equivalent of people that drive big trucks and roll coal, right? I mean, that's really just what this means is G is 1-to-1, right? We say that I is injective if given a 1-to-1 map here and any map down here, then there exists an H from B to I such that doing G, then H is the same thing as doing F. Show the following conditions are equivalent. I is an injective R module. So it makes this work. Every short exact sequence of the form I, B, C to 0 is split exact, right? So if you have a short exact sequence and I is injective, that means it automatically has a split. And finally, the last condition is if I is a submodule of the R module B, then I is actually a direct summing of it. So in other words, if I is contained in B as a submodule, then B is isomorphic to I sum J for some common thing. So think about that stuff. Let me know if you need any help. Any questions on that? Okay. Yeah. So yeah, that problem about the basins, different sizes, right? Okay, this is what we were talking about last time. This is a module F satisfying one against all of the above conditions is called. So I know you like category theories, but it's like it's three objects in category or objects, whatever you might have some later. But this is what we call free module. Basically, I like this a couple of ways. It's any module that has a basis. And I like this equivalent characterization because what it says is I completely understand every free module, right? At least over commute, right? Because F is isomorphic to a direct sum of some number of columns of R. And with, for example, a commutative ring, or more generally, any ring that has a commutative ring is a homomorphic image, the size of the number of copies will be well defined. For the example that you do in the homework, this is not well defined, right? Well, there are many ways that you can write. You write the example I asked you for R is isomorphic to R sum R, isomorphic to R sum R sum R, and so forth. But with most nice rings, there's only one size of the index set that works for a given F. One of the things that's cool about this is I immediately understand a whole linear algebra now, because what's linear algebra? Linear algebra is module theory over a field. And in that situation, every module is a vector space. Every module has a basis. Every module free, that is. So any vector space, I don't care what it is isomorphic to some number of copies of R. Some of these are easy to see. This is shorthand for this. Right. C. This is a complex real vector space. This is an as vector space. Consider set F from 0, 1 into R such that F is continuous. And there are a whole bunch of them. But this is a real vector space, right? Real vector space. Here's what it looks like. I love being so simple-minded, right? This is a pretty complicated thing. As a vector space, this is basically this. Shoot, I can remove the word continuous, and then you've got a whole bunch of functions. Still a real vector space, right? Probably with a bigger index set, right? Corollary. Q is not a real vector space. This is a more dramatic example than the previous one in your homework, right? Because Q if it were a vector space, would have to be the direct sum of some number of copies of R. Well, Q is not zero, right? So it would have to be at least one copy of R. Q is countable, R is uncountable. Q can't be a vector space, right? So that's some really cool ripoffs that I've got of that right now. Let's prove this. This. So let's first do A implies B. So what do we have? We have a non-empty basis. We want to show that it's an internal direct sum. I think I know what we're going on this one. Let's let X be on a basis. Yeah. And let me point out, if you have any non-zero elements of the vector space F, then there's an obvious map from R to Rx. Theodore was Rx. By the way, notice this is a module, right? It's just all multiples of X. Left multiples of X if you want to generalize. Right? This map is clearly onto, right? Why is it 1 to 1? Well, actually, let me. I might not. Let's change this to X and X. This will be equal. Suppose that R is an internal then Rx is equal to 0. Right? Why is that impossible? Well, it's not impossible. What does that imply that R is 0? This wasn't important. I was a little sloppy the first time. X is an X. What does that mean? X, big X, is a linearly independent set, right? And so and X is in X, then Rx equals 0 implies R equals 0. So, in other words, R and Rx are isomorphic as even left R modules because X comes from the basis, which is a linearly independent set.
Well, what is a module? Is it F with I?
No, I'm just pointing out that as an R module, R and Rx are isomorphic. And I'm going to use here's what's coming. X is a subset of F. Right. So X is in F, but actually comes up with this basis set. And
What's the I?
R is the ring. Right. So this is the module of the ring R. And so the only statement I'm making here is as an R module, R is isomorphic to Rx. Right. And I'm going to use that here today. And in fact, maybe it'll be a little bit more clear now where this is going, because notice my first claim that F is equal to the sum Rx because certainly this containment must hold because every X is an element of F. So we got this. If F is in F, or if alpha is in F, then there exists R1, R2, Rn, and R, and Xi1, Xi2, Xin in the basis X, such that R1 Xi1 plus R n Xin is equal to alpha. And notice this thing, of course, is n the sum Rx. I mean, basically, the statement just says the basis, or this thing that I call basis spans.
Can I ask you, so my question is more like, how do we know that R is a module? A module is a submodule of,
Oh, we don't, but Rx is.
yeah, Rex is. But what,
I didn't claim it was. I said as R modules, R is isomorphic to
So
Rx.
it's not required to be the submodule of.
No, you're right. Yeah, I'm just saying that R is isomorphic.
Yeah.
Yeah, the Rx bit is a submodule.
Yes.
Okay, other questions? Okay, so what I've shown so far is that R is the sum of these internal these submodules. So, or I'm sorry, F is sum of cyclic submodules. Rx. And this is why I did this earlier. These are all isomorphic to R as an R module. And that's where we are now in the part of the B statement is I've got that F is a sum of a family of cyclic R modules, each isomorphic to R as an R module. Got that. What I don't know yet is this a direct sum? Right? This is the missing piece of the puzzle. All right. Well, so this sum is direct. Let X be an X. And suppose alpha is in Rx intersect Ry, where Y is in X, but Y is not equal to its parents. Okay. Well, what does this mean? Alpha lives in Rx, so alpha equals Rx. But it's also equal to R1 Y1 plus RK YK. Or these Y's are distinct elements of whatever's left over in X when you pull it out of the legs. Everybody okay with that? So what do we have? We have Rx. Setting these two things equal, subtracting the right off the left, I get this. But X, Y1, YK are distinct. And X So what conclusion can we come to? Well, X is a basis, right? And so in particular, it's a linearly independent set. So this relation being zero, R, R1, R2. So the sum's directing because the intersection of each one of these submodules with what's generated by everything else is zero. Any questions on it? Okay, I think B implies C is pretty straightforward because the statement of B says it's an internal direct sum of these submodules Rxi. And you just do the reverse of that homomorphism on all the coordinates, and you get F is isomorphic to a direct sum of some copies of R. Right, okay. C implies D. So we have that we've got a module of this form. We need to come up with this crazy crap business about function. So let's come up with this function we have here. I'm going to let F be the direct sum of Ri. Each Ri isomorphic to R is Vi. I'm going to write it that way. So for every I, we have the following diagram. Ri and R and in this injection. Okay. Right. And remember, this is a direct sum, so we have this family of maps from RJ into R, right? We have this is the standard inclusion of the direct sum. Remember this one, you take little RJ and put it into the appropriate coordinate, right? J is in the index there. And what does this give us? This gives us this map phi, makes a diagram. This is using our property of direct sums. And we're going to define X to be this. So I want to have a basis element for every RI indexed here. How do I choose those XIs? each RI is isomorphic to R as an R module. And I am going to choose my XI to be whatever goes to the one. Like, notice the important thing here is as an R module, one is the generator here. XI, because this is an isomorphism, there must be some XI that goes here. XI should function as the generator of RI. That's kind of the thinking behind that. And our function, we've got to build this function. Iota next to F assigns to each cyclic generator, this XI, its image in F. That is to say, iota of xj is equal to ij xj in the brace or I. Now, this function works and makes the diagram cute. Let me show you how the homomorphic works. Now that I've got this set up, what do I have? I have my set X, which is essentially kind of the basis. I've got, and of course, more formally, X shoots this into this direct sum, and really the basis isn't just the X's, it's whatever its image is in this direct sum. Now suppose we have some function, any function, F, when X into your module. So then it's just some modules. And I'm going to give this a notation. We will say that F right, this map has no structure on it other than just it's just a map of sets, it's just a function. So the desired homomorphism okay, I'm going to tell you what it does to a typical element of this direct sum, which is it's called RI. Iota of Xi. And let me recall for you very quickly is that what this does is, or this is over. Remember, a typical element, this should be zero almost everywhere, or well, I should say, almost all of these R's. Because this can only be a finite sum, so almost all of R's are zero. This is, well, somebody tell me what it's got to be, make the diagram. Do a better than big sum. And again, since almost all, but it's all finite, and many of these are out of zero, this is just a finite sum. Right? So this is what it has to be, right? I mean, the RIs are the coefficients here, and what does that do? It looks at this thing and it sees where xi goes, the mi, and that function determines where things go. So is it clear to you all that this is a homomorphism? Well, see, I mean, if you have F bar, sum or I over xi plus sum of or I prime over I xi. Well, what is this? This is just F bar of the sum of Ri plus Ri prime over xi. Right? Because the only thing different here is what the coefficients are. Now, let's read this out. This is Ri plus Ri prime. And I, which is Ri N I plus Ri prime N I, which is equal to F bar sum Ri iota I xi plus F bar sum Ri prime iota I. So it's a homomorphism of abelian groups. F bar of the sum of R I iota xi is equal to R F bar sum R I iota I. But the R pulls out of the sum and it has to pull out of F bar as well. Or well, I probably shouldn't be so flippant about it. This is just RRIM. You can pull the R out of the sum and remove this. So it's a homomorphism, right? And notice that the diagram commutes because this is F bar of XI. Which by definition is like 7.1, which is F of X. There we go. So the diagram. Okay. Any questions so far? Okay, let's get D and Ponce. Okay, so we've got this crazy function here. We want to show that F has a non-empty basis. If you look at out of X, this is a subset of F. And then we'll have a non-empty basis. So first consider, let's first consider, consider the submodel of F generated by uh, X. So this non-answer set is, it's got some image up in F. Look at the submodule generated by that, and let M equal let M be F mod out of X. So I'm going to use this. So now, let F, I want to take a function for F from X into M. And I'm going to define this function to be X and X is zero on the image. Now, why do I do that? Well, I'm using part D here. So I've taken everything to zero, to every element of X to the zero element. Now, consider F bar the function that maps F to F mod IX. It satisfies because F takes every element in X to the zero part, so it's essentially killing this. So this projection takes every alpha to alpha plus its coset, satisfies this. But what else satisfies this? So does the zero homomorphism, right? Because you killed it. By uniqueness, F bar is zero homomorphism. So that must mean that this is zero, right? This projection map is the zero homomorphism. But if a projection map's a zero homomorphism, that quotient has to be zero. So IX spans. Now, so we're on our way to showing that F has a non-empty basis. We just show that this image here spans F. And we want to show now that this is a linearly independent set. So suppose Ix is linearly independent. Consider, I'm going to put a linear dependence relationship here and try to deduce that all the R's are zero. So suppose we have R. Suppose we have R one, X one, R two, X two, plus R n, X n, to zero. Of course, our goal is to show that all those coefficients, all those RIs must be zero. So now what we want to do is I'm going to form the following module. I'm going to define n to be the module exactly n copies bar. And that's not a coincidence there. Of course, that n, I'm building this module on a tool to help with the proof. And what I'm going to define f from x to n. Right. By f f of x alpha is EJ alpha is equal to okay, so what am I trying to do here? I read these basis elements here. And if the basis element, or I read through the elements of x here. If it turns out to be one of these guys, I just let it be EJ. And you all know what I mean by EJ, it's still standard linear alpha notation. It's just all zeros and one in the J slot, right? So I'm trying to do the standard basis for Rn. Here R is a range, not the real numbers necessarily. And if my X alpha is not one of these subscripted i's that appear up here, I just make it zero, so I toss it. Now, the induced homomorphism F bar from F into the direct sum of n copies R or as I call it there, M, has the property that F bar I F bar inclusion Xij equals EJ. Right. for those particular bases. So, and let me, point out that, oh, that should be IJ. And, if the subscripted, if this thing is not one of those IJs, then of course it's zero. I'll let that out here. And hence, F bar of R1 XI1 Rn Xin is zero, which is, of course, the image of this is R1, R2, Rn, and the direct sum R. And so we get exactly what we wanted. R1, R2, Rn, 0. And so from this, we can conclude that our X is a basis. X is plenty independent. So F has a basis. Namely, the image of X in a binary. Let me make a remark. Also, I made a point of talking about non-empty bases here. We can also generalize this a little bit. What do you suppose the free module is? People argue over this a little bit, but what do you suppose the free module on the empty set would be? Or let me be more careful. What do you say? What would gamma might be? Would be the zero module. The basis is empty. So, and of course, the zero module has no basis at all, does it? Because the zero module has no linear independent subset. Corollary. And this is a big one. And this is why we all love free modules. I mean, if any module goes on like ancestry.com or 23andMe, they will look up in their chain and find a free module. Right? Every unitary R module, is the homomorphic image. It's clear from all. And you go further. If you define generated the free module can be chosen by. So not only is every R module homomorphic image a free module, but if it's found units, pick it to be generators all as well. I will do a quick proof of this. That M, the R module, and generated by the set X. Notice that, of course, let me point out that if M is the zero module, it's clearly the homomorphic image. So I'll assume that M is not zero. Of course, M has a generating set. I could just take X to be all the elements of M if I wanted to. It's sloppy. Let F be free on the set S. Right, so for the free module, the only thing that matters is terminology. Right. We know this is free module, it's a direct sum of some number of copies of R. So there's an F bar. How do I know that it's on to? Notice that since F bar iota equals F, then for all X in M, which I consider to be the basis set, F iota X is F of X, which is a generator of M. Right? Notice that M here my F is an inclusion. Inclusion of the basis set here. Notice M is generated by set of X. And so image of F bar contains the set X, therefore image F bar contains what's generated by X. Therefore, image of F bar. So there you go. It's on to, which is what we wanted. So any M is like this. And notice that if X is a finite set, then that module I built was finitely generated, which is kind of cool. So in other words, now in a certain sense, we might understand our modules because every module is a free module modded out by someone. Okay, any questions? Okay, I recommend